Okay, by now you should know how to find areas between two curves, and the next step, usually taken in a calculus class, is to talk about volumes of three-dimensional solids. And I like to start with volumes by known cross sections. So just to give you an idea of what these problems look like, here is a typical one. The region contained by root x, y equals 0, and x equals 9, which is this region down here, and I'll color it yellow. So that is described as the base of a three-dimensional region. And if you were to slice this region, if you were to take a cross-section of this perpendicular to the x-axis, you'll always get a square. So you could kind of visualize this as this weird shaped stick of butter where I'm looking at the top of it. So I'm hovering above the dinner table looking at the top of this butter. And if I were to get a knife and cut this anywhere perpendicular to the x-axis, I will always pull from this piece of butter, from the stick of butter, a square. And so I am attempting horribly. I'm attempting to draw squares coming off the screen at you. So everywhere I cut this, I get a square. The closer to the left I get, the closer to the y-axis, my squares will be smaller. And the closer I get to x equals 9, my squares will be larger. But everywhere I cut this stick of butter, I will have a square. Some people have a hard time visualizing that, and honestly, it's not that big of a deal if you cannot visualize it. The key is knowing what shape the cross-section is. But in an attempt to make this a little bit easier to visualize, I have this guy from our friends at GeoGebra. So here is our square root of x base. This graph right back here that I just kind of made gray, that's the square root of x graph. And we have squares coming up off at you, and those square cross sections in orange, I can kind of move them back and forth, and you can kind of see what it looks like. The closer you get to that right end point, x equals 9, we have a larger square. And the closer we get to the y-axis, we have a smaller square. So you can kind of see what this stick of butter looks like, really weird butter. But there it is. So let's talk about how we would go about finding the volume of this. But before we do that, let's talk about area between curves, because the structure, the idea behind generating volume is very similar to the idea behind generating area. And so I want to remind you how exactly area is accumulated. And by now, you probably would look at this region. We have y equals x squared and y equals 4. And I should say 4. Let's change this. And y equals 4. And by now, hopefully you can just look at that and very quickly, without a whole lot of thought, realize that we're going to do the antiderivative of top minus the bottom. This is a dx problem. And my bounds are starting at x equals -2, going all the way to x equals +2. And then you would work out that antiderivative. But the way we actually accumulate that area, the way it actually is generated, is we are starting way over here on the far left side, and I'm basically measuring the distance from the top to the bottom. I'm looking at every possible place, and I'm measuring the distance from top to bottom. And distance from top to bottom is always top curve minus bottom curve. So that distance will always be 4 minus the bottom, which is on x squared. And I'm finding that distance, the distance between those two y coordinates. And if I keep finding all of those distances, and I move slightly to the left, and I move slightly to the left. I'm going to use my vertical line tool. It'll look a lot better. Here we go. If I keep moving slightly to the left, and I keep finding all of these distances, if I move a little bit to the right, and I find all of these distances, and I add those distances together, as I keep moving, and I find all of these distances, and I add them together, they will eventually paint like a little paintbrush and fill in that entire region and amass the whole area. And so when I'm adding those together, I'm really just taking the sum of all of those distances from top to bottom, and we're finding that sum starting at their first intersection and ending at their last intersection. And in calculus, that summation formula is turned into the squiggle S. We are moving from left to right, and so that would be with a little delta x over here, which translates to the dx. But essentially, you're just finding the length, and the length is one-dimensional, it's only length, but as you move that length from left to right, it turns into the two-dimensional area. So we go from a one dimension, and the antiderivative brings it to 2 dimensions, and that's really what we're going to do with volumes. So let's go back to this volume situation. And what we're going to do is we're going to start way over here, and I'm going to think only about that square. And let's go back to that GeoGebra illustration. And if we look at this square way over here at the beginning, if I find the area of that square and write it down, and then I move 1 pixel to the right and I find the area of that square and I write it down, and then I find the area of this square and write that down. Now I keep finding the area of every single square as I move from pixel to pixel, or from one x coordinate to the very next tiny little bump to the right, and I add all of these squares together. Think of it like we have a whole bunch of squares cut out of paper. If we start stacking these up, if I stack enough of these squares will stack up and add to fill up and create the entire three-dimensional solid, just like a stack of paper would. And so if you add all of these squares together, if you add all of their areas, the sum of their areas creates the volume of your three-dimensional solid. So going back over here, I'm starting, and I want to find the area of this first itty bitty square, and we are finding the area of a square, which is your side length squared, and I'm ultimately going to add all of those up. I'm going to add all of those areas, and in calculus, if we take an infinite number of those areas and we add them together, that turns into an antiderivative of the side length squared. And then the next thing I want to do is realize that my squares, I'm starting over here at x equals 0, and I'm moving to the right. If I'm moving my squares to the right, that is a change in x, which means I'm going to be integrating this with respect to x, which means I have to get the area of my square in terms of x. I cannot do s squared dx. I have to have something in terms of x. So I look at my squares and I realize that the side length of my square is a vertical measure, and the length of anything vertical in the coordinate plane is always top point minus bottom point. So my side is going to be top minus bottom. That is horrible handwriting, but whatever. And my top is on the line or the curve, y equals square root of x. My bottom is on the x-axis, which would be 0. And so for this problem, your side length is just the square root of x. So I take that square root of x, I plug it back into s squared, and this volume is going to be the antiderivative of the square root of x squared with respect to x. Now I have to choose the x's that mark the beginning and the ending of this interval. And I'm starting over here on the left side at x equals 0, and I'm finishing over here at x equals 9. So we're going from 0 to 9. And there is your setup. That if I evaluate that integral, I will get the volume of this weird stick of butter thing. And so I'm going to pause the recording and answer that very quickly for you. It actually turns into a nice antiderivative, and then we'll move on to another problem. And there's our answer of 81/2. So that one cleaned up very nicely. And so I generally don't like to give just kind of steps to follow to answer math questions. I like you to have a little bit more of a thorough understanding. However, with volumes, you will find yourself always going through the same general list of questions. And here they are. And so the first thing you want to do is determine what shape the cross-section is. Now, for these problems, that's going to be really easy because the shape of the cross-section is told to you in the question. Every cross-section is a square, but we are going to get to a section where the cross-section shape is not explicitly given to you, and you have to figure that out. So we're going to determine the shape of the cross-section and the area of that cross-section. So if it's a square, like it just was, we need to make note that the area of a square is side length squared. Determine if it's a dx or a dy problem, or dy or dx, and that's determined by the axis that your cross-sections are perpendicular to. So when this one said every cross-section perpendicular to the x, that right there is telling me that it's a dx problem. So we get the shape and the variable right off the bat. Write the area formula in terms of the correct variable. That was the next one we had here. We had side length squared, but I had to convert that into x's by determining that s is the square root of x. So that's the next thing you want to do. And then the last thing you want to do is find the antiderivative of all of that information, and that's what step D is. So I have two more examples I want to look at, two more examples of volumes by cross-sections. Let's look at this one. The region contained by y equals x squared, y equals 0, and x equals 5. So we are looking right here. I already have the graphs drawn, but I'm going to shade the region. I'm going to get out of the lines a little bit, but it's right over there. Let's get up here in these corners. So there's our region. And let's look for the key information. We want to know what variable, what shape, and what the area of that shape is. And so I'm looking at this for every cross section perpendicular to the x. That tells me immediately that this is a dx problem. I have to think in terms of x. We have a rectangle. So I'm going to go ahead and start thinking rectangle. And I know that the area of a rectangle is base times height. So I always go through these steps anytime I'm doing a volume problem. Then here they tell you the height is twice the base. So if height is twice the base, then I could take that and I could substitute it for height here, and I could rewrite my area formula as base times twice base, which would obviously be 2b squared. So now I have an area of 2b squared, and I know I will eventually need to find the antiderivative of that area, 2b squared, with respect to x, right? But I cannot have b squared in an integral that is a dx problem. So now I've got to figure out what is b. How do I get the base of this rectangle? And let's go back and read the problem. We are cutting it perpendicular to the x. I'll go ahead and do a representative perpendicular cross section. And they tell you that the base is in the region. So that piece I just drew is the base, not the height. So there's my base. If you want to try to draw a three-dimensional representation of this, the height will come off the screen at you like this. And it's kind of a long height. They said the height is twice the base. So it's going to look something like this. It's not very good, but whatever. So there's my height if you want to draw that. But the key is the base is on the coordinate plane from the x-axis up to the graph of y equals x squared. So your base is top x squared. And if you want to kill it dead, you could say minus the bottom. But if you're on the x-axis, that is the line y equals 0. And so my base is simply x squared. So I will take this x squared and I will replace the b with it. And that will give me a new antiderivative of 2x squared squared with respect to x. And I'm almost done. The only thing I have not done is determine the limits of integration. So remember, we are doing everything in terms of x. And so I'm looking for the x coordinate that starts my region, which is at 0, and the x coordinate that ends my region, which is 5. And so there is your integral setup. And evaluating the integral on these problems typically isn't brutal. Sometimes it can be, but they typically are kind of nice. You very seldom run into U sub and stuff like that with these types of volume problems. I'm going to solve this one really quick. And for this one, we should get 1250 for your final answer. So let's look at one more volume by known cross-section. So here we have the first quadrant region contained by e to the x, which I have drawn here, y equals 3, which is that vertical line up here. That is the base of a solid, so I think I'm going to shade that again just so I can visualize that base a little better. So right here, there's my base. And let's look for the key information. Let's see. For every cross-section perpendicular to the y-axis, this is a dy problem, perpendicular to the y-axis. And if you want to, you can go ahead and draw a representative cross-section right there. Draw something perpendicular to the y-axis. And here's the shape, an equilateral triangle. Now, this is one you may not be able to yet, at this moment, spit out the area, but the area of an equilateral triangle, the area, you can go 1/2 base times height, but getting the height is very tricky. The base would be this section right here in the plane. However, the height is tricky. Another formula for the area of an equilateral triangle is side squared times the square root of 3 over 4. So jot that down in your notes. Probably be quicker to commit that to memory so you don't have to look it up every single time you run into these. But that is the formula for the area of an equilateral triangle. I know this is a dy problem, so I can go ahead and set up my integral. It's the antiderivative. That is a horrible squiggle S. Whatever, there we go. Antiderivative of side length squared, square root of 3 over 4. And this will be done with respect to y. And now the challenge is, can you get the side length? Can you get s to be in terms of y? So can s be in terms of y? and my side length is right here. I've already drawn one. This is one of the side lengths, and if you want to try to draw the triangle, this is an equilateral triangle coming off the screen pointing at you. So I'm going to draw it a little bit flat to try to mimic the three-dimensional behavior. Not really necessary to draw them, but each one of these side lengths is the same. And here we have a bit of a problem. We have a bit of a problem because the side length does go out to this graph, y equals e to the x. However, e to the x is not in terms of y. I have to have an equation in terms of y. So I'm not going to do e to the x. We have to take this and solve that for x. And so if y equals e to the x, you should know that x is going to be the natural log of y. To undo the e part, you use a natural log. So that's the equation we have to think of. And whenever you identify that we have a dy situation, go ahead and make sure all of your equations are in terms of y at that moment. Go ahead and get it out of the way, because if you don't do it at the beginning, you might forget to in the end. So my side length is actually the natural log of y, and I will substitute that into s here. And when I do that, I'm going to also take this square root of 3 over 4 out of the integral. That is a constant that is not really helping me a whole lot in the integral. I'm going to take out the s. I'm going to replace it with a natural log of y. This is dy. And now for the limits of integration, I need the y coordinates that determine the beginning and ending of the region. So now I'm looking across the y-axis, and I'm starting right here. That one's not explicitly given to us. The upper one is. And this one, if we're talking about e to the x, you should know that e to the x crosses the y-axis at 1. And so there is your integral that would find the volume of this. And if you look at the instructions on this problem, it says set up, but do not evaluate. And the reason we're not evaluating that is because the antiderivative of natural log y, natural log y squared, is quite cumbersome and tricky. So we're just going to look at this one and admire its beauty. And there is your antiderivative that would give this volume.